In this video tutorial, we're going to discuss modeling procedures for a flat slab, a uniform thickness slab in ADAPT-SOG with post-tensioning. We'll go ahead and in our splash screen, we're going to select the option for SOG. We'll note that here the only available mode is PTRC. We need to have the availability for tendon modeling, and we'll be working in US unit system. In the UI, I'm going to first navigate down to the bottom plane, and I'll just set up a slab using an arbitrary grid. So we'll say that this is just 10 by 10 feet. And from the modeling window, we can go ahead and model components. So here we're going to model a uniform thickness slab, and we're going to assume that this slab is, let's say, 60 feet by 100 feet, and we're going to have some stepping in the slab on one end. If we need to adjust the slab, let's assume we need to put a notch on another side, I can always select the slab, right click, and insert additional points to move to different positions. So maybe we have a notch, something like this. Okay, the next step will be to create a soil support. So we'll go over to, again, modeling. We're going to select the option for supports, and we're going to select an area spring. And this can be placed around the slab like so. Okay, we're going to go back and adjust this after we model and just check the model for validation. We'll go back and adjust this for the center lift condition, but for now we'll leave it in this position. The next thing we'll do is add post-tensioning. So we're going to assume for this slab we're going to change the thickness. I'll double click on the slab, and we're going to say that this is a 5-inch thick slab. Under criteria, we'll change the concrete if needed. Here this is 4,000 psi concrete. I'll leave that as is. For pre-stressing, we can set up our pre-stressing defaults for the material shown here. We're going to be using 1/2-inch diameter unbonded cables, and we'll say OK. We'll leave that alone. I'll go over to tendon, and I'm going to start modeling the post-tensioning. So we'll go ahead and add a cable, and I'll add one on this edge. So I'll use the snap tools, and we're going to snap from point to point. You'll notice that this actually snapped outside of the slab, so I'll backspace and make sure I select the proper point, and then I can press enter to close. And you can see that if we double click on this tendon, we can open the properties. We're modeling this just as a straight line, no swerving in plane. The area is 0.153. The number of strands we're going to say is 1 tendon per line, so we could double it, triple it, however many we want here, but for a slab on ground we typically just model each individual tendon. We can assume an effective force. This force might actually be dropped down a bit to account for any friction loss due to the interaction with the soil, which the program doesn't capture. So you may want to adjust the effective force. You could also model the calculated force and have the program directly calculate the friction loss due to the tendon shape inside of the concrete. So another way to mimic the loss due to the friction interaction with the soil would be to adjust the stressing here, or you could also adjust the force given. This is the jacking stress or stress given. So we'll use the effective force method. And then the shape of the cable by default is a reverse parabola. I'll change this to straight, and it's anchored at 2.5 and 2.5. Okay, and we'll go ahead and copy this over. So I'm going to use the modify ribbon to copy. We're going to select copy, and I'm going to model these. I'm going to model a tendon at enough spacing to provide the pre-compression in the slab that I want. So sometimes we just have prescriptive spacing requirements, but we're going to at least check to make sure that this feeds enough pre-compression into the slab. So we'll assume the tendons we modeled every 3 feet. If we take the 3 feet, 36 inches times the depth of the slab 5, and let's assume my target pre-compression for the slab is 75 psi, that's going to require a force of 13.5 kips. So technically we could model, right now our tendon is set to 26.7 kips per line. We could space these tendons every 6 feet to get the 75 psi pre-compression in the slab. We're going to go ahead and just use the 3 feet because we're going to use that assuming that we need it to control, let's say, flexural stress rather than just meet the pre-compression requirement. So we'll go ahead and say we're going to space this every 3 feet in the positive X direction, and I'll enter 35 tendons, and I'll go ahead and copy those. Okay, now some of these need to stretch, so we can take these tendons here, and under the tendon toolbar I can trim and extend tendons. But the dimension to trim has to be set to a much greater height, so I can go over to tendon settings, and this distance we're going to say, let's just say it's 30 feet. And now I'll try to trim extend again, and those I'll trim out to the edge. These two tendons, you can see, actually trim back to the closer edge, so I'm just going to delete those. They're now overlapped. And I'll go back and reassign this tendon. Back under modify, we will go back to by coordinates and select 3, and then we'll do this every, let's say every 12. Delete those two. And you can see, because I have the trim set to 30 feet, it automatically trims back to the slab edge. That's a pretty high trim tolerance. I would go back and reset that to something more reasonable after you've modeled the cables. Okay, so we have our tendons every 3 feet in this direction. I'm going to go ahead and save this. And I'll go now and model the tendons in the Y direction. So I'll add a tendon. Again, by default, when I add a new tendon, it will be a reverse parabola, and I'll have to change the properties again to a straight shape. Once I've set the properties, I can now copy that tendon vertically. So if I go back and change my tendon settings, I'll change this back to, let's do 25 feet. These steps here, we're going to assume once we get beyond here, beyond that edge, this is more than, that's actually more than 25. So let's change it to 40 feet, see if that works for us. So we'll copy that. I'll go to modify, and we're going to use a positive Y direction. And we'll say that this is 30 copies. And you can see by manipulating the trim, you easily get the tendons in the slab in the model. Otherwise, you can post trim and extend tendons like we had done the first iteration when we had checked that. We're going to now jump over to loading. We have all of our tendons in our slab. If we rotate this to like a 3D view, you can see we have a few quick access viewing states down on the bottom. You can also go to home, and in home we can use the option maybe to rotate the slab. This would allow us to rotate and view the slab. We could go to visibility under render model, and this is also a nice view to check just to see and confirm geometry. So we could go to a wireframe, for example, and I'll scale the slab vertically by a factor of 5, and you can see this is now the PT layout in the slab. Okay, so what we'll do now is add some loading to the slab. We're just going to add uniform load. There's several load types. We could add point loads, line loads, patch loads. We can also use wizards. So we can add loads by use of mapping to a slab edge that has been selected. So I'll select this slab edge, and we're going to add for the patch load. Live load I'm going to say is 0.04. And then for my line load, I'm going to say that my line load is a dead load, and there's 500 pounds per foot on the perimeter. Okay, and these are the loads. If we rotate, we can view loads. I can go to the loading toolbar to turn loads off and on. I can turn only the line loads on, double click to see and change a load if needed. I can turn on only the patch loads, and then to drill down further into loading and what can be viewed for loads, we can go to the load settings. We could show, for example, dimensions, and that will give us a view of the actual magnitude of the load that's been displayed. Okay, I'll turn the loads off now. And before we start manipulating the soil support for the center lift condition, we're going to just mesh and analyze and make sure this thing runs as is. So we'll go to Analysis. I'm going to mesh the slab, and I'll just use a simplified approach to mesh. I will turn off the tendons in the tendon toolbar, and then we're going to analyze. So under loading combinations, you can see there's one service combo here. That's the combination we'll use to evaluate the stresses in the slab. You could add additional combinations if needed. The program is used to check serviceability requirements of a post-tension slab on ground, so there's no option to design reinforcement for a non-structural slab on ground. In this case, if you wanted to design reinforcement, you'd have to use a program like ADAPT-MAT in order to design the rebar for the center lift condition. The edge lift condition requires the ability to place line and point displacements, and so SOG has the capability to model line and point displacements here, whereas ADAPT-MAT does not. So for the edge lift condition, you couldn't mimic this particular type of design because of the lack of the displacements in that module. Okay, under Analysis, we'll execute the analysis for service. I'll go ahead and just run this. Once we're done running, we can select yes to save the solution, and I'll just take a quick check on the deformed shape, and it should be uniform. We have uniform load and a uniform spring, so there's really no differential displacement at any region in the slab, aside from the perimeter where we have we do have a line load on the perimeter. So we've selected the service combo under loads. I'll go to Analysis, and we will check the Z direction displacement. So you can see we get higher displacements out on the perimeter where the contour goes from 0.01 to 0.04. And to view this, what we can do is go back to our render model, and if I go to a warped shape, this shows me the deformed shape of the slab. This is under fully supported spring condition. But what we want to do is we want to set the spring equal to the edge moisture distance. And the edge moisture distance, EM, is typically given by a soils report or just site conditions that have been evaluated. So we're going to make some just arbitrary assignments for EM. I'll go ahead and just close the result display settings now. And I want to turn off the shell elements. I can always go back to my default display, which is set up under View Settings, or I can go to Analysis and turn off the elements here from the visibility panel. That turns the elements off. You can still see we have the scale shown. That requires me to actually go back to the settings here and just turn off this takes you back and clears everything. So we'll now close that. Now this pink region for the area spring will actually become something like this. It's just an offset of the slab edge. And we're saying that this offset initially, A is equal to EM. This is for the center lift condition, CL. And if we follow the guide in the program manual, if I go into this program manual, this is the ADAPT-SOG manual, and I'll just find this flowchart. Here we have our flowchart here on page 23 of the manual, and we're going to first set A equal to EM. In our case, we're going to assume EM equals 5 feet. So we need somehow a way to model that soil support at 5 feet in the program. We'll come back into this interface, and because we have a non-rectangular or non-square slab, this becomes a little more time-consuming in terms of how we can do this, but it requires the use of construction tools, construction lines. So I'll create a construction line. You could also import a CAD file that allows you to more rapidly import, let's say, multiple offsets of the soil spring. So I could take this shape and then offset it in AutoCAD and then import that back into ADAPT so I can just trace over. Here I'm just using construction lines, and I'll set these up. Okay, and I'm going to offset these. So I'll offset this one, and we're going to go ahead under Modify. This is going to be -5 feet. We'll say Move. I'll take this one and this one. And this will be +5 feet. I'll move again. This is going to be a +5 in the Y, so we'll move that. And then finally we have the last edge that moves to the -X direction. So we have 4 movements of the different lines, the construction lines. This is say -5, and move. Okay, and then we might have to create additional lines like so to have these intersect. So this would come up to here, and so everything intersects now. I have something that I can now realign this to, and I'll go ahead and I'm just actually going to delete this first. We'll go back to Model, and I will just create a new support, and I'll use Snap to Intersection to snap on these points. I've turned off Snap Orthogonal, and we'll just wrap this around the perimeter of the inboard from the perimeter of the slab. Okay, so now we have our soil support. Again, A equals EM. This gap is called A. And our first pass at the solution, we're going to say that equals the 5 feet. And we can define the edge displacements, or the different parameters, soil parameters rather, in this dialog. So this is used to calculate the calculated displacements for edge lift, but we're going to store these here. We'll say that edge lift is 5, the expected movement is 1 inch, and then for edge lift, this is for center lift, the edge moisture distance for edge lift we're going to say is 7.5, and the vertical movement is 1.5. Okay, so now we have our model with tendons, slab, loads, and the proper soil support. And we'll go back and we're going to reanalyze. We're going to execute the analysis. And this comes from this step, analyze the foundation and determine what the deflection is. So we'll analyze this again. Now we're going to have more severe deflection on the perimeter because it's unsupported by the soil in this run. And if we turn on our deflected shape, you can see that the deflection is 1.31. And our YM value is 1. So based on values that might be derived from just empirical formulas that are being entered now into a finite element solution, we have somewhat of a miscorrelation between the actual response of the slab under the loading and what was predicted for the edge moisture and calculated for edge moisture and for the vertical movement. So in our flowchart, we say, okay, the deflection is greater than 1/3 YM. The 1/3 YM represents the target where we want to use that target to determine whether or not the solution is correlated, and we can go into the route of checking the different stresses. Here, our actual displacement is greater than the predicted vertical movement. That means that the slab edge would be pressing into the soil and basically be acting like a permeable membrane, which it's not. So we need to now adjust our assumption for A, and we're going to reduce it by say 20% and then rerun the solution. Okay, and we'll go back. And we said, well, this is 5 feet. I'm actually going to cut it down half because I know that 1.31 is quite a bit greater than 1. It's 31% more. So in order for us to get down to 1/3 YM to 0.33, we're likely going to have to go through multiple iterations. Okay, so we'll go ahead and turn off the solution. I'm going to select this soil spring, and I'm going to cut it down to 2.5. And you can see when I do that, I have this little X and Y dimension. I can use this. The tolerance right now is about, I think, 1/10 of an inch. So I'm going to escape out of that just for a moment, go over to Home. Under Settings, I'll go to Dynamic Dimensioning Settings, and we're going to say the increment is going to be not 1/2 of an inch, but we'll say every 6 inches. Okay, so we want to move this, and I'll just kind of do a rough estimate. I don't want to have to reposition these lines. We could, that would be the more proper way to do it, but we'll just kind of use our belt and suspenders approach and move these down to 2.5 inches here. And this might represent maybe 2 or 3 iterations, but we're just cutting that in half and saying, well, we know we have to come down this far anyway in terms of the offset to get a workable solution. So we reduce the offset and we rerun the analysis in order to correlate the proper edge moisture distance with the expected vertical movement and response of the slab. In this particular run, we now have 0.39. So this is close enough for us to continue on and check stresses. We're now kind of entering this branch of the flowchart. We'll assume that this is met, and now we're going to check flexural bending stress. We want to check shear stress, and we know that we're going to meet precompression because we calculated that up front manually. So we'll check precompression, but all 3 of these checks have to be done using support lines, or let's say design strips, we call them. So support lines are used to develop design strips, and we're going to space support lines for uniform slab just some uniform width. It's a representative width, and we'll use 5 feet for our example today. I'll come back over to the model, and I'll again clear that result. I'm going to go ahead and clear these lines. I can go over to Home and turn on my layers and just say, okay, these adapt lines I don't want to see. I'll just turn that layer off. They're still there, but I would have to turn the layer back on. We have tendons set up, and similar to how tendons were laid out, we're going to lay out support lines, but these are going to be laid out let's say every 5 feet. They don't technically have to follow the same spacing as the cables. We could also do every 10 feet. Every 15 feet is probably too much for a slab of this size. So if you have a really large slab, 200 by 300, let's say 15 feet would be sufficient, but here we're going to scale it back down, and we're going to use 5-foot strips. So I'll turn off my tendons, and I'm going to go over to floor design. We're going to select the X option for strip modeling, and I'll go ahead and model my support line. And I'm just going to go end to end, and I'll take this, and similar to tendons, I'm going to copy that. So I'll copy this vertically, go to modify, and we're going to copy, and this will be a 5-foot offset, and I'll do 20 copies of that. And that was just a guess. I'll just delete out these other points. I can't even remember how wide the slab is or the overall dimensions. We'll now take these, and unlike tendons, I can't really trim and extend automatically, but I can turn on perpendicular and just stretch these out to my edges. So this is easy enough. We'll readjust the length of the support line. I'll select this last one and move that up to there, and then for these ones I need to trim these back like so. Those are the X support lines. Now I'll do the Y support lines. So back under floor design, I'll create this support line, and I'm going to copy that support line. This will be every 5 feet. Here we'll say 35 copies. And you'll notice I copied that in the wrong direction. So we'll delete that. Should have been in the positive. Try that again. In this direction. 5 feet in the y, X direction, positive. That's following this global convention for the X and Y axes. And then we'll say this is 35. Okay, we'll delete out those we don't need. And then again we have to readjust the position of the support lines. You can manually enter all of these if you want. We don't have to copy them, but usually it's a little bit faster to just copy the lines and then adjust them as needed. So we'll finish these last 3 support lines, and then we'll be done with our support line modeling. Now the support lines, if we double click on these, we have properties that are related to the support line. First, the support line direction. So support lines cannot intersect if they're labeled the same direction. In other words, I couldn't model all of the support lines in this model as X because you would have intersecting lines. So we've added one group as X, one group as Y. It's a two-way slab essentially, and we're checking the strips in either direction. Secondly, we'll go to design. These are being designed and evaluated really as two-way slabs in the sense of the stress allowable, and that's defined in the criteria. We'll show that here in a moment. Design section options. The distance between 2 points is defined as a span, so here we have maximum number of design sections per span set to 12. This is too coarse for how we modeled the support lines, so we're going to change this, and we're going to say we're going to use 40 section cuts per span. Essentially, each line will be split into 40 design cuts. And I'll go ahead and now under the floor design we're going to generate the design sections, and this generates the design cuts, and you can see the program is showing design cuts for both directions, but you'll notice this is the only design strip that actually was changed to 40. Everything else remained at its default of 12. So we need to make sure if we ever change multiple items at the same time, I can select all of my support lines. I'll go to Modify, Selection, and under Support Line I'm going to change the maximum number here to 40. That changes all of them, and I'll regenerate the strips here. Okay, we're going to use the Strip Results Visibility panel over here to control the visibility display of the strips. So I'll turn off all directions, X and Y, turn on all directions, and I can turn on X, turn on Y. So each one of these now support lines is converted into a design strip based on half the distance to the next adjacent support line in terms of how it develops the tributary region. And after we've modeled the support lines, I can design the sections. This allows us to check things like flexural stress, shear stress, and precompression. So each of the different sections is now uniquely designed. Once the section is designed, we can now review results graphically. So the first thing we want to check is the precompression. I'll go and under loads, we're going to look at service. I'm going to select the display option and then set my minimum precompression to 75. Okay, and if we go back to analyze or analysis under design sections, stresses, we can check P over A. And clearly, everything that's shown as green, which is all of the sections, they all pass for precompression. This is based on the FEM result versus a non-FEM based result, which is the number of tendons cutting through the strip, and that's this result. So this looks more uniform because it's not subject to any axial restraint in the plane of the slab. You can see we have some differences. We have kind of a pattern forming. We have a support line here, and every third support line is low. And all that means is that the spacing of tendons, you get kind of a tendon, there's also one here on the edge, you get more tendons being contributed to this strip and this strip versus this strip. So the repetitive pattern of the tendons just falls such that two of the strips get more tendons cutting through it than the third strip. So that will happen if you have this option for precompression number of tendons being used, because it's all based on the number of tendons cutting through a design strip. If we were to turn on the tendons and overlay that, here we can see like this section cut right here has 2 tendons, this one has 2, this one actually only has 1 because of the pattern. This skips over this edge of the support line, and that kind of repeats itself. That's okay, we can always rely on the FEM. This is not subject to the position of the tendon. It's subject to what's the precompression, what's the axial load in the slab due to the post-tensioning. If we go back to the results here and I turn on the numerical display, we're going to be able to see all of our values along the strips. So you can see the precompression in this slab is up around 150. And that was, apparent when we had first entered the model. We said, okay, we could really space these tendons at 6 feet and get the right, precompression, but we chose to limit it to 3 feet. If we want to flip directions, we can always flip the direction now to this side, and we can see the precompression in the X direction. So precompression for this slab is met. I also want to check flexural stress. Here's actually a couple of sections, I didn't see these, that are not passing precompression. So if we turn on the tendons, we have a tendon actually that stops right there. That tendon needs to move out to there. If I move a tendon, I have to reanalyze and redesign sections in order to update the results. In this case, we're going to continue reviewing the results, but that once I update the analysis and the design of the sections, this area would then come into compliance with the precompression. We're going to now jump over to flexural stress. So back on our flowchart, we're going to check the precompression first, because we want to meet minimum precompression before we do anything else, and then I'll come back up here and we're going to check the flexural stress and the shear stress. So the flexural stress, if we look at the way that this behaves under center lift, if there's an increase in volume of the soil on the perimeter of the slab, then the slab is going to basically do something like this, which means that the top fiber would be in tension, the bottom fiber is in compression, and so we're expecting at the top to have tensile stress and at the bottom to have compressive stress, unless we have so much post-tensioning in the slab that that's overcome and you get a reversal. So if I look at the top stress, you can see that the top values are actually pretty high. These are all in compression. Okay, this is the top flexural stress. The bottom stress is also in compression. So in this case, if I was to look at one of these design cuts, all of these cuts are actually fully pre-compressed. And we'll try to illustrate this. If I look at a design cut and I have, let's say, a situation, typically when we bend this piece of concrete, again, we get tension in the top, compression. If I take a cut through there, we might get a stress distribution that looks like this. This is compression, this is tension. This is purely based on the flexural component. And then we add in, let's say, the P over A. And the P over A, we have something that looks like this. This is all compression. And so this, if we add this up, you know, that we might have something that looks like this. We have a tiny bit of tension and a lot of compression. In our case, we start off with something that is already fully pre-compressed potentially. So in our case, we might actually get something that we have very little tension due to the bending component, and maybe this line is actually, you know, here. Maybe it's actually out here like so. When you add in the pre-compression, you get a trapezoidal shape like this. So this is in compression, that's less compression than the bottom fiber. That's what's happening in our slab. So in essence, it works because the slab is fully pre-compressed. There is no tension. The allowable tension stress is under criteria. And if we go over here to allowable stresses, you can see that the allowable is based on 6 times square root of F prime C. Well, our compressive stress is just a multiple of F prime C, so it's hovering around, let's say, 1750 psi, and clearly our compressive stress is less than that. We have a few out here that are fairly high on the perimeter where we get the drop or the drop off in the soil support. We get peak stress where we lose contact with the soil. And if I go back to floor design and just go to the next direction, the Y direction, we get similar behavior. The bottom stress is in compression, as is the top for the most part. In this direction, it's a little bit different. We actually get tension out here. You can see this positive. There's a reversal. There's an inflection point in the stress. So here we're getting some tension, in the other direction we're not. This tension, however, is less than 6 square root of F prime C, and that value for this slab, that target is 379 psi. So all of these tensile stresses are less than allowable. Therefore, the program flags the section as green. If it was out of bounds, if it was greater than that, then we would have to make manipulation. We would have to do something to bring the stress back into compliance, and that might mean we have to thicken the slab. It might mean we have to add more posttensioning to the slab, or do something else, increase the allowable stress, something that brings us into compliance with the design criteria and parameters for the design of the slab. Okay, lastly, we can check shear stress. Now, shear stress is not checked through this dialog. We have to go up to what's called builder sum. And I'll open and launch builder sum, and this lists all of our support lines. So in each support line, if we click on this and go to the stress diagram, we can see in this stress diagram, we can check average stress, that's precompression, top and bottom stresses, that's what we showed earlier on the graphs for flexural stress, and then finally shear stress. So the shear allowable, this line, is dictated by an allowable stress formula that's based in that dialog we looked at earlier for allowable stresses. The green is the actual diagram, and we can go through and check these individually. Another way of doing a uniform slab, we know that every cut in our slab is 5 inches deep, and all the cuts are also 5 feet wide, except for the perimeters where it's 2.5 feet wide. So we have basically 2 cuts we have to check manually if you wanted to do this more holistically versus looking at every line. So if I turn on the diagram for stress, or for shear action rather, under shear action, I can see my diagram, and my maximum and minimum shear stresses are shown here. This is for either direction, X or Y. So I say, okay, I have 4.52 kips, and if I take 4.52 kips and I divide it by, I'll just use the minimum width of a design cut, 2.5 feet. If I divide 4.5 by 30 inches, that's the 2.5 feet, times the effective depth, we'll assume it's 3.75. and I divide that, I get a shear stress of 40 psi. Under the criteria allowable stresses, the shear stress is 1.7 square root f prime c plus 0.2 times precompression. So we'll calculate this. If I take 1.7 times 4,000 square root, that's already 107 psi. I don't even need to worry about the part from precompression because that exceeds my maximum shear stress using the minimum width of the strip. So that's a way to also check this kind of manually, but do it much quicker than checking each of the different design cuts. All right, so that's center lift. Now for edge lift, we have to basically convert the model. And edge lift, what we're going to do, let me go back over to the flow chart. We're going to jump down to the edge lift flow chart. And in this flow chart, we're going to apply an edge displacement. So we have to calculate an edge displacement. We call it delta, and we apply that to the slab. Well, once we apply an edge displacement to the slab, the actual deflection on the perimeter will equal the edge displacement. So we're going to actually start down here. We want to make sure that the A, which in our case is 7.5 feet, is greater than 3 times EM. Well, what is EM? EM is actually the 7.5 feet. A in this case is the separation distance between where the slab loses contact with the soil and where it contacts the soil. So if you have a slab and you might have a contour that looks like this, and inside this area we have contact, so A would actually be, you know, the greatest of these distances away from the perimeter of the slab. This is A. EM is whatever the edge moisture is for that given condition. So for edge lift, for this particular slab, we're assuming EM is 7.5 feet. So we're going to move the slab, or excuse me, move the soil out to the perimeter of the slab. I'll go back to my default display, and I need to turn back on my soil spring, and I'll take this and I'll move it. Okay, so we move this out to the edge of the slab. And there's a PTI formula that allows us to calculate the edge displacement, and that can be calculated here. We can go for each slab edge, we can calculate its own edge displacement. So for example, I'll just do 2 edge displacements here. We'll say for this slab along this run, and I need to go ahead and dimension a couple of these so I can see what the dimension is. Go to home, and I'm going to add a dimension from there to there, and then I'll add this one. And then the total dimension this direction is 60 feet. Okay, so let me save this as a different name. We're going to save this as SOG flat, and we'll differentiate it as edge lift. Going back into the criteria for edge displacements, we're going to just do 2 slab edges, the long side and the other side, and this side here we'll say. Now each one of these technically would have its own value calculated. I'll just show you, assuming that we're doing this, and let's say this is its own edge displacement. So the slab with uniform thickness, slab length normal to the edge is actually 60 feet. Length of the slab we'll say is 110. The slab thickness is 5. The perimeter loading we said was 0.5. Then we have an importance ratio, where we place more importance on displacement, which is a function of the inertia, and precompression, which is a function of the area. So this formula that was developed by PTI, if we go back to our flowchart here. This formula is geared towards ribbed slabs, and in this manual we describe what K is and how to calculate and apply K. So because it's a function of ribbed slabs, we have to basically provide this importance factor. And this states that if the axial stress of the centroid of the foundation and its equivalent will be the same. Okay, so if K equals 1, deflection is kind of governing the design. If K equals 0, then stress kind of governs the design. And we know that deflection doesn't govern, so we're going to set this equal to 0. I'll calculate. If I was to set it equal to 1, you can see the displacement to apply is quite high. So we'll calculate 0. And by the way, if we put help here, or select help, this also dictates and tells you kind of what dictates for each of the different governing conditions. Moment of inertia governs versus precompression. So we'll use a displacement of 2.68 inches for this slab edge. That's the top slab edge, and then slab edge 1 is going to be this slab edge here. So normal to that slab edge we'll say is 110, and then this might be 60. Again, we have thickness of 5, 0.5, and importance ratio we say is 0. So this is 3.5 on this edge, and we're going to say 2.5 on the other edge. Okay, that's what's calculated. If you were to calculate these per this equation here, then this is what you would end up with. But this equation has spacing of interior stiffening beams. Again, it's relative to a ribbed slab, not a uniform thickness slab. So we have to recalibrate it to uniform thickness based on the K factor. I'll go now to model displacements. We're going to do line displacements, and I'll go to properties of the displacement. We'll use a displacement here. This is going to be negative 2.5. And I'll take that along these edges. Now again, each of these edges would have its own displacement. I'm just calculating a couple of them and then adding these here. So just to show the process, and then this might be 3.5. Once I've entered the displacements, we're going to reanalyze. I'm going to remesh the slab, and then I'll execute the analysis. And we're going to now check the separation distance. So if I go back to my top view, I'll go back to default display and check my deformation. You can see this black line is actually where we have contact with the soil. So my target is 3 times EM. If I'm greater than 22.5 feet, 3 times 7.5, this distance, then we need to reduce the edge displacement by 20% and continue reducing like we did for center lift. And I can easily take dimensions. I can go ahead and just go from this point out to this point. That's 16 feet. From here over to here is 35 feet. So right away we have to reduce the edge displacement. Once we whittle that edge displacement down such that this gap is no more than 3 times EM per this spreadsheet here, or this flowchart, then we go back into the same process. We check flexural stress. We've already checked precompression. We know that that works, but we would check flexural stress, shear stress again, just like we did for center lift, using the exact same methodology where we design the cuts based on this solution. So now we have a situation where we're mimicking volume change at the perimeter of the slab. So the slab curls up. We have now tension on the bottom and compression on the top. It's reverse of the center lift condition. And we'll assume that this is a correct solution, even though we would have a few more iterations. Okay, I'll go back and turn this off, and I want to turn on my stresses. And I'll go down here to Design Sections, Stress, and I'm going to look at the bottom stress. And you can see there's several locations in the bottom where I don't meet the tensile stress. Now this is an invalid solution, but again, just showing the process, we would want to check the stresses. In this case, we have kind of peak stress out on the corners. And what that might be caused from is the fact that we're forcing a deformed state of a corner upward using these applied displacements. Well, in reality, as the volume changes at this location, that corner or joint might develop cracking to relieve, stress that's developed by the uplift of the slab. So you can't have this corner really deform the way that we're forcing it to under displacement. So to relieve that type of condition, what we would recommend the user do is take these edge displacements and we would pull them off the corner. Let's say that we pull these off by, let's say, 2 feet. I put them from point of the edge to point of the edge, but we'll pull them all off by 2 feet. So we leave a gap that allows the slab to be unrestrained at that position. And I would, again, take all of these and just model them with a 2-foot offset like so. And this is where we would pull those back to. Okay, so that is the process for an edge lift conversion from a center lift model. If you have more questions on modeling slabs on ground, please contact support@adaptsoft.com.